Let's talk about diode. And let's define it. A diode is a two-terminal electronic component with asymmetric conductance. We'll explain in a minute what is the asymmetric conductance is. It has low, ideally speaking, should be zero, but it has low resistance to current in one direction and high, ideally infinite, resistance in the other. And this is the asymmetric aspect that I mentioned before. Let's look at the symbol and kind of a physical presentation of a diode. On the top is basically a physical presentation of a diode. We have the anode on the left-hand side and the cathode on the right-hand side, and the current flows from the anode to the cathode. One way. It's like a one-way street. Current cannot flow from cathode back to anode. Only one way from anode to cathode. And the symbol, the electronic symbol, is presented on the bottom. It has kind of a triangular with that line, which basically blocking the electricity from the cathode to the anode. And the main function, the most common function of a diode, we still in the definition of it, is to allow an electric current to pass in one direction, and it calls the diode forward direction from the anode to the cathode, while blocking current in the opposite direction, the reverse direction. Thus, the diode can be viewed as an electronic version of a check valve, just like a check valve. This unidirectional behavior is called rectification and is used to convert alternating current AC to direct current DC. The sketch on the left presents to us very kind of clearly and simply that the current can go one way from right to left on the top picture, from the anode to the cathode, and it cannot go the other way. That means on the right hand side, that means that if I actually put a sine wave into the anode, wants to let the current, this AC current, go through the diode, and that particular sine wave, half of it is positive and half of it is negative, as like we said priorly in the course, that diode will be forward direction, will be positive and allow the current to flow through from anode to cathode only 50% of the time. Only when the sign is above the zero axis, only when the potential is positive, this is where the current flows through the anode. It does not flow when the potential is negative. And this is why we can see on the graph on the bottom that it's basically the diode blocking all the negative voltages, because basically the current is in the other way, is in the other direction, is in the reverse direction of the diode. The picture on the right hand side presents to us several situations. And well, I want to start with you on the right hand side. The right hand side meaning we have a diode D2, and this D2, the cathode of D2 is connected to a resistor, which in turn connects to plus 5 volts, and the anode of the diode D2 is connected to ground. It means that the anode has a lower level of voltage, lower potential than what it is in the cathode. That means that the current wants to flow from the power supply, the plus 5, down to ground, but the diode blocks it. And when it blocks it, the internal resistance of the diode is so high, practically speaking, as we can see on the far right, it's basically like a cutoff. So current cannot flow from the power supply to ground in the case of D2. However, in the case of D1, when the potential of the anode of D1 is greater than the potential of the ground, which is 0, then current can flow. When current can flow through the diode from the anode to the cathode, and ideally the internal resistance, like we said before, is 0, it's like a short. So it's like visibly we can actually see as it actually disappears, and there's a short instead of. So it is equivalent ideally that we have a 5 volt through a 1K resistor through a short down to ground, and the current can flow. Why? Because it's forward direction. The set of diodes that are presented on the left hand side actually demonstrate to us that as long as the voltage level on the anodes are bigger than the voltage level of the cathodes, it will actually allow the conductance of the current. If it's the other way around, the current will not be able to conduct. Now, later on in the seminar, we'll talk about the difference in the potentials between anode and cathode. What should be the minimal difference in order for these diodes to conduct or not to conduct? And we just got to this particular point, and I want to mention very, very specifically that there are two technologies of making diodes, as making any kind of semiconductors: germanium and silicon. Silicon is more popular, more commonly used, and the difference between anode and cathode should be at least 0.7 volt DC in order to let this diode conduct current through it. The anode should be at least higher than 0.7 volt than the cathode in order for it to conduct. Germanium is 0.3 volt, but it's, like I said, it's less commonly used. Let's look at the picture on the right hand side. Because basically we have a semiconductor device that has a P and an N and a PN junction in between, as we can see on the top left corner. And that particular internal diode, pure internal diode inside it, P and N, has 0.7 on them, across them, as a voltage drop on that particular diode. Each diode basically holds on it in the positive direction, in silicon, 0.7 volts. That means that on the far right picture, if I put three diodes in the same direction in series, on each there is a 0.7 volt drop. So altogether 3 times 0.7 is 2.1 volt voltage drop across the three of them. And if I start with plus 10 volts in a voltage going through a resistor, we can calculate very easily the resistance and the current of that particular circuit. Again, silicon, meaning that between the anode and the cathode, there should be at least 0.7 volt difference in order for the diodes to conduct. On the second picture from the right, we see 3 diodes. They are still in series, but we take outputs of different voltages from each branch, what you call. We branch out 3 times. Again, when we branch out 3 times, every single diode on itself take 0.7 in order to conduct, and it's a fixed level of voltage. It's a fixed number, 0.7 in silicon. Then we can actually have a voltage divider. We start with 10 volts going down to 0. There is a resistor that has a voltage drop upon it, which is depending on the current, and on 3 branches that has 0.7 difference between each diode and another. So very easily you can actually divide the voltage into certain levels according to the needs of the functionality of the electronic schematic. Let's look at the center of the picture when we see the IV graph, the behavior of a diode. We have the first quadrant number 1, which is a forward operating area, and we have the quadrant number 3, which is the reversed operating area region. In the forward operating, when we pass the 0.7, when the difference in potential between the anode and the cathode is 0.7 in silicon, when we just cross that line, when the potential is greater than 0.7, then current can flow, and very high current can flow very easily. The internal resistance of the diode is very low, current can flow. However, quadrant number 3, because we need 0.7 anode to be higher at least than the cathode, when we actually reverse it, there's just a leakage current that flows through, and very, very negative voltage still just the diode holds it upon itself, and the only current that flows through is very minute value of leakage current. It's not like in quadrant number 2 that the current actually can flow because the internal resistance is very, very low. On quadrant number 3, the internal resistance is very high. Mega ohms, ideally it should be infinite. A specific type of diode is a Zener diode, and let's define it. The Zener diode is like a general purpose signal diode consisting of a silicon PN junction. Silicon, more commonly used, it can be also germanium, but let's concentrate on silicon. Silicon, remember, 0.7 between anode and cathode. When biased in the forward direction, it behaves just like a normal signal diode, passing the rated current. We are actually working in this particular situation on quadrant number 1. But as soon as the reverse voltage applied across the Zener diode exceeds the rated voltage of the device itself, it's specified in the technical specification, the diode's breakdown voltage is reached, at which point a process called avalanche breakdown occurs. At that point, a current starts to flow through the diode to limit this increase in voltage. First of all, the symbol in the center, we see the symbol, it's slightly different than the simple signal diode, and we have the two small bars on the diode to distinguish between this and a regular diode. But let's look at the graph. Let's look at the behavior, the IV characteristics of the diode on the right-hand side. And let's look at the quadrant number 1. It behaves just like a simple diode. But I want to concentrate with you right now on quadrant number 3. In quadrant number 3, any specific Zener diode has a specific avalanche breakdown point. And when the voltage is reversed and the voltage level of the cathode is greater than the voltage level of the anode, then the voltage across the Zener will be fixed. Fixed based on what is written in a technical specification of the Zener diode itself. So there are Zener diodes that can, in a reversed polarity, they can hold 5 volts, 5.5 volts, 6 volts. Every Zener diode will have its own avalanche point. That means the voltage across, even in a reverse direction, will be fixed and can be used further on the electronic schematic. Let's look at it. This is basically the point, as we can see right now, of the reverse voltage. We are actually now in the quadrant number 3. The voltage is reversed to the point where the diode actually becomes kind of a battery, holding upon itself this voltage up until the avalanche point. And from that avalanche point, there's a current that flows, again, to limit the increase of the voltage, which means that there's a voltage, fixed level of voltage across the diode, and it's basically stabilized. No matter what happens in the input, every time that input voltage to the Zener diode, in a reverse direction, goes beyond, goes above, goes more than what is specified for the Zener, This will, the value specified in the technical specification will be the maximum that the Zener can hold across it. So the voltage drop of the Zener itself will be fixed in reverse mode. Let's talk about the clipping effect of a Zener diode. Because we know now that any Zener diode has its own what you call breakdown point or avalanche point, which is the point that the voltage across the Zener will be permanent, will be fixed. A Zener diode can actually does clipping, and the way it does clipping is as it's presented in the drawings that we have here on the slide. Let's actually evaluate what's happening in the top one. We have a generator, AC generator, that actually generates sine wave. And this sine wave goes, on the positive side, goes through a resistor, reverse direction on the, through the Zener diode, and when the voltage level of the sine wave goes above the rated voltage breakdown of the Zener, then the Zener actually breaks down and it holds upon itself that particular voltage. And this voltage is fixed. So we can see the waveform in the output on the right hand side, then the top part of the sine wave is basically clipped. That level of the clipping is the rated level in the technical specification of the Zener diode. Now, when the sine wave is in the negative, crossing the zero, going negative, then the diode is actually positive direction conductance, which behaves just as a regular diode, just as a regular signal diode, not a Zener diode. And because there is a 0.7 in silicon that has a voltage across, fixed voltage level in a positive direction, we have, according based and look at the red arrow, we have this 0 volt voltage drop across the diode in the positive. So it's clipping the top above the rated voltage of the Zener diode, and it has a permanent fixed 0.7 volt in the positive direction. So it's an asymmetrical type of waveform when we have only one Zener diode. However, the bottom picture shows us two back-to-back cathode-to-cathode Zeners, which makes the operation basically symmetrical. Let's analyze that. We have a sine wave coming in. When the positive side of the sine wave goes through the resistor, the upper diode, Zener diode, will conduct, and the lower Zener diode will actually block it up to the rated voltage specified in the technical specification. That means that it will be plus 0.7, which is the contribution of the top diode, plus the voltage, the fixed voltage of the bottom diode. This will actually this will determine the clipping level, above which everything will be wiped out, clipped. On the other direction, when the sine wave actually goes negative, crossing the zero axis, going negative, then the bottom diode conduct drops 0.7 across it, and the top diode basically does not conduct up to the point of that rated voltage, again specified in the technical specification. And the same explanation as I described before holds actually in this case also. So this is the reason we get a symmetrical waveform at the output, as opposed to the top one. Now, because this Zener diode, from the point of the avalanche, from the breakdown point, basically holds fixed voltage level across it, we can actually use the Zener diode to regulate variations of voltages coming into it. Let's read it together. By passing a small current through the diode from a voltage source, via a suitable current limiting resistor, the Zener diode will conduct sufficiently current to maintain a voltage drop of V out. So that Zener has a fixed V out, and that V out goes out to the load, whatever the load is, based on the electronic circuitry. A voltage regulator circuit can be designed using a Zener diode to maintain a constant DC output across the load in spite of variations in the input voltage or changes in the load current. So anything that happens on both sides of the Zener diode, because there is a constant DC output voltage across the between the anode and the cathode of the Zener diode, again based on the specific Zener diode technical specification, it basically eliminates the variations, number one, in the input voltage, number two, in behaviors of the loads at the output. Light emitting diode, LED. It's a specific type of a diode. Just like a Zener was a specific type of diode for certain features, light emitting diode, LEDs, are also diodes, but for another specific type of applications. Let's define it. It is a two-lead semiconductor light source. A LED is basically a light source. It is a basic PN junction diode, just from the structure of it, the content of it, similar to regular signal diode, which emits light when activated. This is the difference. When a fitting voltage is applied to the leads, electrons are able to recombine with electron holes within the device, releasing energy in the form of photons, and this is the light that we see. And the color of that light, and corresponding to the energy, the intensity of the energy, the level of the energy of the photons, is determined by the energy band gap of the semiconductor itself. Let's look at the bottom. First of all, on the left-hand side, we have the symbol, the electronic symbol. You see a regular type of, symbolically, a diode, but with the two arrows, meaning that it emits light. The physical shape is it's presented in the middle, and on the right-hand side, it's basically the content and the structure of the LED itself, and we can see that there is a cathode and a anode right in between, in the center of the volume of the LED, and the reflector right next to them, in order to reflect the photons which are being generated and released. If we look at the internal structure and content of that particular PN junction, just like a regular diode, we have that junction itself, the PN junction. Look at the center of that particular picture. In the P-type, we have the holes. In the N-type, we have the electrons. And there is a junction in between, which is a region where the holes and the electrons basically combine together. They actually flow and they recombine. This recombination generates photons, generate energy that can be seen by the photons. There is a limited light that coming out from the junction, not from the N-type side and not from the P-type side, but from the junction itself. We can see the current flow direction. It's from the P to the N. And again, light is emitted only where the area, the junction, where the electrons meet the holes. Now, based on Ohm's law, and we've covered Ohm's law in this course, if, for example, given 20 milliamps current and 2 VDC, volt DC, to light up the LED, a limiting resistor is calculated. We have basically to limit the current, so not to burn the LED. And typically LED needs anywhere between 10 milliamps to 20 milliamps to actually light up, to emit light. And the way we can do it is by having, for example, in the picture on the left, we have a Vs, which is the source, the voltage of the source. It gives us voltage across a limiting resistor and a positive direction diode LED connected to it. Based on Ohm's law, the resistance is the Vs minus V forward. V forward, remember, silicon is 0.7 volts, divided by the current. The current we want to limit it to 20 milliamps. That's what the LED needs. And the Vf is 0.7. We know that. So we can calculate the resistance. The picture on the right, the electronic schematic on the right, is kind of another example. Now with the numbers. Across the LEDs there are 2 volts. The minimum, I recall, is the 0.7 volts need in order to conduct, but it can actually have 2 volts upon it. If we start with 12 volts in the battery and we need 0.2 amps, which is 20 milliamps, and the voltage across the LED is 2 volts, that leaves 10 volts across the resistor. So 20 milliamps, 10 volts across the resistor, we can calculate the resistor itself based on Ohm's law. And this is a presentation of typical light-up currents. Look at the 3 levels. We have a battery. This battery is connected to an LED, and it's connected in series to an ammeter, which will give us the amount of currents in amps or in milliamps that the LED needs, and it's connected in series to a limiting resistor in order to limit the current, not to burn down the LED. And you can see the difference in the brightness, the intensity of the emission of light of the LED in different levels of current going through, which are basically determined by the resistors. So the R3, when the resistor is 330 ohms, because we have a battery with 9 volts, it gives up 20 milliamps, and the LED will actually emit light the most.